buying generation, they are also producing electrical energy, or specifically due to the abundance of solar. And lastly, since we have this type of integration, we need to also have investment in terms of what we call cyber asset or cyber physical system. This would be including Internet of Things, or let's say smart meters and communication system. So that is why our grid is becoming complex. Due to this reason, our data become also intense, or data intensity, from forecasting from the different meters and different transmission nodes or distribution nodes, to stream operational data, and lastly, to representation of this digital asset in terms of cloud services, or let's say digital dashboard. That is why we also are burdened with what we call the optimization problem. The scheduling of the power plants, the proper scheduling of batteries, as well as the uncertainty problems of renewable energy, demand, and also electricity price. Because of this, we also need to have faster and smarter search to see what would be the optimized operation of our power grid. So the question now is no longer whether discipline should converge. The question is, how do we do it responsibly and productively? So what is it like working in quantum computing and engineering? So in practice, you try to consider topics such as mathematics, computer science, physics, or even electrical engineering concepts. Most work today in this field consider what we call hybrid classical models. So we do not consider only classical approaches. We also consider trying to include quantum or quantum-inspired solver. But the main problem is the translation, meaning to say how you translate real engineering problems to be reformulated to fit these computational frameworks. So there is different progress in coming up of these iterations, benchmarking, as well as realism about the current hardware. So because of this, we could see engineering professions or non-physics majors could be able to be considered here in quantum computing. Specifically, engineers could bring system intuition, constraints, or even operational priorities. Example would be some of those power system problems, which are rich in optimization structure as well as uncertainty. So the need for domain knowledge for these specified problems are required and is very useful when we try to do those objective functions and constraints. And that is why application-driven research is how we try to move quantum from novelty to value. So we have already all of those concepts. What we are now going to is how do we apply these quantum concepts or quantum principles to something that could be of value or something that could be applied directly. So that is what we call application-driven research. So when you are talking about quantum computing, as of today, we could put that into 4 points. We consider qubits, wherein that is how we represent data. We could consider the principle of superposition, wherein this is how we represent waves from the different deterministic classical state. We consider entanglement, which we encode the relationships between variables in a more useful algorithms. But as of now, we are already near what we call the reality of NISQ era, wherein we try to be in a state wherein these applications that consider those noisy could be applied already for quantum chemistry, optimization, machine learning. And power engineering problems specifically focus on optimization problems and machine learning. So where do power engineering work or could be put to? In terms of data, this is in terms of our SCADA, PMUs, power measurement units, or the electricity market, or even weather data. In terms of model, we consider modeling our power system or our grid. We try to also look into the aspect of the digital twins. In terms of formulation, we could say we consider the objective functions as well as decision variables. In terms of solvers, we have already classical solvers, we have already hybrid quantum-inspired solvers, or even quantum computers. And in terms of decision, what we are trying to see or what we are trying to decide is more on what would be the schedule of the generators. When would there be possible blackouts? What would be our planning mechanism if there are brownouts? What would happen if there are also maintenance scheduling? What would happen if there is a sudden typhoon that hit our transmission network? So all of those is the decisions that we made when we talk about power engineering. So quantum, I'm not saying quantum would be a replacement. Quantum is not a replacement. It is just an additional computational layer with this broader workflow. Meaning to say, we could use the principle of quantum computing when we talk about data. We could also put that in terms of models. We could put that in terms of mathematical formulations. We could put that in terms of the solver itself, or even in terms of how do we try to search for the decision. So there are actual research already that have been done in terms of power engineering problems. So some of those I'll be showing in the next slides, and I'll try to explain it more in layman's term, what does each of these research topic talks about. So here's first topic. This is one of the papers by my co-author in the Kuryente project, Dylan, which is solar irradiance forecasting using a hybrid quantum neural network, a comparison of GPU-based workflow development platforms. So in this paper, they try to create a comparative analysis between the different platforms in forecasting the solar irradiance. So why do we need to forecast solar irradiance? This is essential when we talk about PV systems, specifically what the uncertainty of PV, when do we need to have this capacity. So based on the given results of the study, it could be found out that there would be a decrease in training time when we use the platform CUDA-Q compared to other applicable development platforms such as Torch Quantum and Penny Lane. But in terms of which they have a comparable RMSE compared to the other two. So this is just a comparative analysis. Another paper, this is more on in terms of stability assessment. Majority of the power grid runs with power plants. Our power plants have this what we call electrical generators or electrical machines. When we have those electrical machines, they tend to consider what we call inertia. So this inertia would cause yung tinatawag natin na frequency sa system natin, wherein we'll try to make it as stable as possible. So in this paper, they try to consider this variational Gaussian gate level gate to try to have this machine learning approach to consider the stability of the given power system network. So they apply this into a test system. I think this is an IEEE 115 bus system. They also try this to an existing local grid in China. And they found out that after a certain number of iterations, they could already classify whether there is a stability problem or there is no stability problem. So that is another example of applying quantum computing into the power engineering workflow. This is more on the feature detection or identification if there is a problem or not. This is another one. This is more on in terms of its communication paradigm. So it's a quantum distributed unit commitment, an application in microgrid. So what they did here is they applied the quantum circuit before putting it into a classical computer or classical computing approach, wherein it just shows how the different microgrid communicate with one another and to itself in terms of what we call the Lagrange function. This Lagrange function is more on in terms of the costing. So this unit commitment model, which is a classical approach, would be converted into certain translated paradigm that would be able to be included to a quantum circuit. Afterwards, it would be going back to the classical computing. So what would be the output is that there would be an optimized generation of power as well as a receiving of power through each of the microgrid system. So a microgrid is just simply a smaller power system. This could be as small as just a residential house with a PV system that would try to communicate with another residential house. So there is a possibility like that in the other areas. And here, this is more on mathematical extensive, wherein we try to convert our classical unit commitment problem, which is a mixed integer quadratic problem, into a quadratic binary problem, or into a quadratic binary problem, and also into a quadratic unconstrained binary optimization problem. The need for this one is because you could not be able to put the classical mathematical model into a QA solver. You need to convert that into a Kubo model, and this Kubo model would be the one that will be putting inside our quantum computer. Okay, in the result shows that as we try to increase the number of units, there would be also an increase in time, but the result would be almost the same. There would be just a limitation around 8 units to 12 units. So this is the current state as of the writing of the paper. So they applied that into a D-Wave 2000Q computer. This one is more of a local publication. So we try to have what we call the quantum computing inspired unit commitment reformulation via Cubo. And we could see that the comparison between the Cubo, the quadratic binary programming, and also the mixed integer quadratic programming, we could see that the Cubo model has a lower objective value compared to the QBP and MIQ when we talk about smaller power grid, and it has also lower solving latency time. On the other hand, when we did medium power grid, we could also see that there is also a drastic decrease in the price of or the objective value compared to the QBP, but MIQP has still the lowest objective value. But in terms of solving latency, we could see as lower time for Cubo models. Okay. So from those studies, we could already establish what are the roles today, as well as why could we pair that naturally with quantum. So for instance, when we talk about load forecasting, electricity price forecasting, renewable generation forecasting, AI creates better state estimates and forecasts for downstream optimization. So we could already have what we call yung quantum plus AI natin. In terms of fault detection, anomaly detection, and condition monitoring, since you could not do the actual fault detection in actual bigger systems, we could include what we call a digital twin. A digital twin would be a test bed for this algorithm validation. In terms of decision support for scheduling or dispatch of renewable energies, conventional generators, batteries, fuel cells, we could have what we call hybrid workforce. that could route these sub-problems to the best available solver. And lastly, existing digital twins for simulation, monitoring, and operator insights could require what we call the data governance and engineering judgment. So we could see already that intelligence systems are already being reshaping in our uh, timeline now. Okay. So with that, we have what we call first project here in the Philippines that focus on uh, power system problem, specifically the Corriente project. So the Corriente project is quantum computing based forecasting and optimization applied to electric power grid. So the main reason why we've formulated or conceptualized this problem is because as we look at the field in manufacturing or even in some of the goals of IBM, they focus more on this mathematical optimization. At the same time, we could see that in the Philippine Energy Plan, this flexibility of generation is also considered as one of those main power problem in the power industry. So with that, we try to have a solution. So the solution of the project is to have what we call an industrial proof of concept. We try to use what we call the hybrid quantum predictive analytics and prescriptive analytics approach that would be retrofitted for the business needs of the given electrical industry or electrical partner through what we call the socio-economic study. At the same time, the project also aims to develop some supporting activities to further enhance the knowledge of professionals as well as the academe and the students in terms of writing a position paper, proof of concept proof of concept documents, conference publication, socio-economic study, and also capacity building. So the project has just different configurations. So we start with data collection, which we try to have what we call the hybrid quantum forecasting model that could be done and integrated next to what we call the hybrid quantum unit commitment modeling, then to a hybrid quantum robust optimization. So this part talks about the experimentation and prototyping. Now, from the given aspect, we try to validate that through the industry by having a socio-economic study, hypothesis testing, and also business and standard testing and validation through our partners, the Bottleneck One, and one of our collaborators, the Department of Energy. That is in terms of the power engineering aspect. Now, where do quantum aspect goes? It goes on more if we try to have this model already inputted to simulated, analog, or digital quantum computing testing. So we could use the different available solvers or workspace available already. So that could be CUDA Quantum, D-Wave, Fujitsu, or whatever that is already applicable in the market. Then from there, we could already validate the operations through what we call the hybrid quantum software as service approach. So I'll be not diving into deep with this part since the project is still ongoing. That would be one of the key outputs of this Corriente project. Another output of the this Corriente project would be the establishment of KISLAB. So KISLAB is Quantum and Intelligent System Laboratory for Power Engineering, wherein we try to focus more on the topics such as hybrid quantum computing in terms of machine learning and optimization in the field of power and energy. But still, we try to also consider classical computing. That would be machine learning, artificial intelligence, and optimization in the field of also of power engineering. Or in just a layman's term, this is just a practical combinational tools for energy system. This laboratory aims to have what we call the quantum energy ecosystem maybe by 2030 onwards. So when we talk about quantum energy systems, we talk about smart support decision systems, smart energy management and protection system that integrate other emerging technologies such as real-time simulations, edge computing, Internet of Things, with algorithms from operation, with engineering principles such as operation research, data analytics, that could be mixed to quantum computing topics. So when we talk about quantum energy systems, we talk about the power producers. This considers what we call generation expansion planning, generation hosting capacity. When we talk about planning, how many generators do we need in the future? How many PV panels, PV systems do we need to integrate? How many wind turbines? Or what would happen if a certain distribution company include 10 megawatts of PV system in their, or 10 kilowatts of system into their distribution network. So that is what we call the hosting and planning capacity. We could also consider virtual power plants. We could also try to look at the aspect of machine learning or artificial intelligence in terms of energy resource discovery and forecasting. So that is in terms of power producers. We have also what we call the electricity market, the wholesale electricity spot market here in the Philippines, wherein we could try to predict what would happen to the electricity price in terms of generation and demand. What would be, we could also go into the other aspect, the energy transaction security, wherein we could consider blockchain combined with quantum computing principles. Or we could go to energy trading platforms. And lastly, we could have what we call the rolling unit commitment or real-time commitment strategy. Another very sensitive topic right now would be the increase in energy price, increase of price of diesel and gasoline. So we are expected to have to consider the use of e-vehicles in the future, specifically the energy transport. So what would happen if, let's say, for a certain area, there would be an abundance of charging station? So charging station is not the same as a PV system or not the same as a conventional generator. There is a certain time that they could be having a demand. There would be also certain time that they could not have demand. So we would be considering also the proper placement of this charging station. We need to also consider where would be the proper traffic layout if we try to see that we talk about EV taxis. So those are the things that we talk about energy transport. And lastly, the conventional power system operation could also be used, such as what would be our decision support, how do we make our protection system more smarter or more intelligent, expansion of substation, congestion planning, optimal power flow, and reliability assessment. So from those things that we have seen, what would be the value for the industry? So we could say we could have better scheduling. We could have better reserve allocation. We could have a more multi-objective decision support. So we could expect improvement in the operation of our power grids. In terms of planning, we could look at the scenario analysis of the distributed energy resource growth, storage, and even network upgrades. In terms of the market, since there is a richer forecasting and optimization, there would be more encouragement for market participation and there would be also lower risk. And lastly, in terms of our existing infrastructure, digital twins and analytics could be included for a more resilient and intelligent asset. So this near-term value is likely to come from the given targets, benchmarks, or hybrid solution. And this is not hype-driven replacement for existing operational system. So we will not be replacing the existing. We are just trying to integrate it more. That is what we call convergence of the system. In terms of academe or researchers, here are some of the possible opportunities and collaborations. So in terms of research opportunities, we could already consider benchmarking real power problems, not only toy abstraction. We could also consider uncertainty aware and scalable formulation. We could build digital twins and data set that could be supported by reproducibility. And we could link this novelty with the possible relevance in the operation of the grid. For collaboration, this would, as what I have said a while ago, it is not just one field that would benefit here. We could have joint projects with electrical engineering, computer science, applied math, and even physics. The funding would also be one of the things that we could be seeing, as this is also aligned with our priorities in terms of national policies as well as emerging technology. There could be also consideration for industry partnership. Specifically, we could already apply those constraints and we could validate already our possible algorithm developments. Lastly, students would also be able to have a training into these hybrid tools, and they would be also having more communication with the other fields of courses or cross-disciplinary communication. For my case, this is my case, this would be more on what would be my current research interest. So it's more on quantum and quantum inspired optimization, smart grids and modern power system operation, load forecasting using hybrid machine learning, renewable energy integration, storage and resilience, digital twins for infrastructure monitoring and decision support. So here we could say that we want to have an advanced computational or computation useful for a real energy system. All of these research interests or all of these research topics goes down to what we call usefulness for real energy systems. Okay. So last two slides. So my advice for those researchers that would try to enter this field, we always start with the fundamentals. So go back to your linear algebra, optimization, probability and statistic, and programming. But you need to use your domain strength. What non-physics and engineering majors could do is bring this real system constraints and performance system. And do not already start with quantum computing. We could start first with quantum-inspired or hybrid methods before we expect the direct quantum hardware advantage. You also need to have collaboration with other disciplines, since it would be more rewarding and more useful compared to having it already isolated into a specified specialist. And lastly, benchmark rigorously. Compare your research with classical baseline and state your limit honestly. So do not overpromise. Do not give false claims. So always try to benchmark with classical models or classical baseline. So I think this is the second to the slides. I think this is the last slide. Modern power engineering will be shaped by teams that can connect physical infrastructures, intelligent system, and advanced computation. So the laboratory positioned this convergence not as speculation, but as a research and engineering agenda grounded in real power system challenges. Okay, and with that, I think it's just 30 minutes. So thank you for listening. If you have some questions or clarifications, feel free to maybe chat or raise your hand. Thank you very much.
Yeah. Thank you so much, Dr. Gerard. So if anyone has any questions, feel free to send them in the Zoom chat, or you can also raise your hand if you want to unmute. So we had a very ano no, insightful talk na mas practical, I guess, compared to our previous talks. And ang witty din ng mga project names, no, Kuryente tsaka Kislab. Ayan, we have our first question from Vincent. In the near future, how wild the world will be, everything we do is run by quantum. Ah, okay. Di pala siya question. My bad. Sorry. Okay, first question from Jabez. Would it be easy to implement these from the perspective of adoption and policy?
Okay, thank you for that question, Jabez. So, in terms of adoption and policy, I think, again, there are already initiatives that been doing here in the Philippines. So, I think next week meron tayo uh, sa Quantum Readiness Workshop. I think it's 23 and 24 sa DAP. But yeah, it boils down kasi na hindi lang naman kasi isa ang when we talk about an emerging technology, it's not only about the scientists, the engineers, or those that are talking about this. We need to also involve those policymakers as well as sabihin natin yung mga mismong may hawak yung mga certain application. So, medyo that would be the hard part. But what we could do as those that trying to go in this field is try to be able to translate to them in a practical manner or let's say in more simple manner kung ano ba ibig sabihin ng quantum computing. So, I have a lot of experiences talking about quantum computing, lalo na doon sa mga walang, sabihin natin, limited knowledge. So, there are some misconceptions that we need to try to translate sa kanila. So, it's more on how we communicate. Kaya napaka-importante yun. Okay, for the next question, for that case, once we have already translated yung model, we'll try to look, since we are limited sa budget namin sa DOST, we'll try to look at subscription aspects. So, depende kung ano yung mag-fit do sa budget yung tinitingnan namin, as well as yung uh, technical limitation also of the translated. So, we are trying to look at, there is also yung sa yes, it's always try to go back sa classical muna. Kasi as of now, pwede natin sabihin na meron nga tayong there is already, but ang problem kasi, ang ating validation is always first with classical models before we push through with yung hybrid quantum or quantum inspired or even yung quantum models natin. So yun, I hope I answer yung question, but I'll just give updates na lang once na nakita namin na yung mga comparison kung ano yung magamit. Yes, we could also we're also doing yun yung ML. Okay, next question. Are infra ready for the intelligence power system? Okay, for this case, when we talk about the Philippines itself, medyo we are lagging behind. The Philippines is lagging behind in terms of uh, the existing network infrastructure. Right now, I think niro-roll out pa lang nila yung mga smart meters or even yung mga digital meters. And in terms of PV naman, ang meron pa rin tayo ngayong problem is papunta pa lang tayo sa net metering. So ano ba ibig sabihin ng net metering? So this would be yung ability na pwede ka na rin mag-bring back nung nakuha mong power do sa PV papunta sa grid. So in terms of infrastructure ready, I'm not yet sure if the Philippines could have it as of now, but maybe in the near future, I'm hoping positively na makapag-adjust na tayo doon.
Thank you, sir. Question from me naman, where can we get updates kaya from for your current projects?
For that, currently, ginagawa pa kasi namin yung aming social media page. Wala kasi kaming social media manager. So, I'll be giving, maybe I'll be giving na lang sa later on yung aming social media page for that. So, but yeah, we're trying to also hype up yung aming social media page so that there would be more awareness in terms of the Kuryente project as well as the Kisla.
Yes,
So baka
siguro
merong
can
gustong mag-volunteer also to be our social media manager. That would be also, sabihin natin, much appreciated.
baka
Okay,
may
so,
gustong mag-volunteer. Okay, go sir.
okay, what kinds of research are you doing right now po sa lab nyo? So currently, uh, we have we have here yung more on sa we have electricity price prediction, we have also yung demand forecasting, we have also yung solar irradiance as well as wind speed. Then we could also consider yung we have also a certain part na we're considering yung unit commitment problems for a certain electric cooperative. So, yun yung mga current research. Then, one of my advices sa masters is doing a reliability assessment problem using uh, quantum Monte Carlo simulation. So, those are actually yung mga research as of now. So, but I'm open to other research as what I've shown a while ago. Okay? How big is the data? For now, since we have limitation in terms of and we are limited sa project itself, we're considering only, I think 10 years data of 5-minute resolution for demand, electricity price, wind speed, and solar irradiance. Then yung sa wind speed and solar irradiance, may mga features pa kami kino-consider. We also consider typhoon data. Since yung problem namin is more centered or focused on a given electric cooperative, dun lang muna siya. Kung ano man yung existing nun. So once we have validated and presented that to the Department of Energy as well as yung cooperative namin and they find it acceptable or valid, we could scale it up. So pag nag-scale up tayo, we could consider other types. So yun. Pwede ma-consider rin yung mga hydro, pwede rin ma-consider yung mga solar and yung mga geothermal and etc. And maybe nuclear, yes. Also nuclear. I think nuclear is also another thing na tinitingnan rin sa energy system ngayon.
Again, thank you so much, Doc. Do you have any other questions from the audience?
Let me just stop sharing yung screen ko.
Any other questions? If not, yeah. From Sir Burns, where do you publish your work and is that accessible? Do you have a Google Scholar,
You
perhaps?
could see my Google Scholar but mostly sa mga IEEE transactions as well as Elsevier. But for yung existing works, we have currently, I think, two papers that are already that are being submitted. One is energy reports. So hoping na ma-publish siya doon sa energy reports. Another one is, I think, sa Journal of Cleaner Energy and some conference papers. So more or less, once they are accepted, within end of this year, I'll be sharing them naman.
Okay, thank you so much, Doc. And yeah, siguro last call for questions and I'll be sharing my screen now. Um, but yeah, if we don't have any more questions, we can present our certificate of appreciation to Doc. So this certificate acknowledges that Dr. Gerard Francesco Apolinario has masterfully shared insights as a speaker in World Quantum Week Spotlight Talk, a webinar in celebration of World Quantum Day, signed by engineer Ethel Joy Badyang and Mr. Bobby Corpus Jr. So if we can, for the participants and also our speaker, can we turn on our, turn on our cameras for a picture taking? So this is our last talk for the morning, and we'll have another one in the evening. So if you can turn on your cams now, just for a quick picture taking with everyone.
Awesome.
And
I'll take the photo in one, two, three, smile. Isa pa po. One, two, three, smile. All right. Thanks so much.
all right, thank you so much, Dr. Gerard. Yeah, so if you have any questions, I think feel free to reach out to either Dr. Gerard directly or to the QCSP team, and we can forward your questions to him. But yeah, so once again, we have our evaluation form here, and we would greatly appreciate any feedback on this session. And I'll also be sending the link in the Zoom chat. And yeah, once again, we'll have our last spotlight talk later from 8 to 9 p.m. So I hope you all are excited for that, and we hope to see you again later. And yeah, so once you finish answering the evaluation form, you may leave unless you have any other questions. But yeah, this has been Monica, and I think our host Ethan a while ago has also left. So we thank you very much for attending this morning, and we hope to see you later.